For more than a century, scientists have been fascinated by the concept of black holes. This idea began to gain significant focus in 1916. Of these, a few of the celestial anomalies remain the most fascinating and mysterious phenomena we've discovered, residing at the meeting place of enormous gravitational forces and an elusive nature that defies our comprehension. A black hole, which may or may not have a mass between 2 and 4 million times that of our Sun, remains a mysterious enigma persisting throughout the universe. Even after decades of concentrated research, our understanding has evolved from nearly nothing to gradually assembling additional information, using new advancements that are still emerging. A.M. Yakubu's most recent discovery has disclosed shocking details about black hole interiors that could conceivably challenge established beliefs and present novel perspectives on these celestial objects. This new information opens up pathways for more in-depth research into previously overlooked aspects. Join us as we delve further into the captivating universe of black holes and discover what may be concealed in the vast cosmos. Before entering Yakubu's latest findings, it's important to take a look back at what we already know about black holes. Despite the fact that most people have a basic understanding of black holes, key elements remain ambiguous. In 1916, Albert Einstein's groundbreaking general theory of relativity predicted that black holes existed. At that time, the idea was purely theoretical. It wouldn't be until around 50 years later that concrete evidence confirmed black holes are real. This confirmation arrived in the 1960s during studies of the celestial body Cygnus X-1, a bright source of X-rays. These X-rays were more than just random, they were drawn into an impenetrable mass. This dense mass, later identified as a black hole, completely altered our perspective on the cosmos. The discovery was groundbreaking, demonstrating that black holes are not just real but elusive objects requiring further research. After this revelation, scientists from all over the world launched a collaborative effort to learn more about black holes. As a result, the realization emerged that the Milky Way itself may contain approximately 1 million black holes. However, due to their extremely difficult nature to identify, this estimate remains speculative. While black hole detection is extremely difficult, skeptical scientists believe these massive bodies number in the millions, hidden away in our galaxy, making it even more essential to comprehend their properties. Let's break down the fundamental idea of gravity. Black holes exert such extreme gravitational forces that everything within their domain is crushed into a singularity, a point where the very laws of physics break down. Simply put, black holes function like gigantic vacuum cleaners, drawing in everything. One of the most terrifying aspects of black hole research is the thought of someone falling into one. As they approach the singularity, they would be stretched apart by immense gravitational forces, ultimately torn to pieces before complete annihilation. When damage occurs, it's best to remain at a safe distance. Despite black holes being dispersed across the universe, the nearest one is nearly 500 light-years away, still a concern. In 2021, researchers made a significant achievement by securing the first clear image of the M87 black hole. After numerous nights spent photographing and compiling images, they revealed a black hole that allowed for deeper study. As researchers gathered more data, they discovered that black holes consist of 3 distinct layers. Contrary to widespread belief that black holes are merely voids, these layers are essential to comprehending their structure. The first layer is the event horizon, the point beyond which nothing can escape the black hole. When something crosses this line, it is inevitably drawn in. The second layer, known as the photon sphere, is where light becomes trapped due to the black hole's intense gravitational pull. Finally, there is the singularity, the point at which all matter is reduced to an infinitesimally small size, where the very fabric of reality collapses and physics as we know it ceases to function. Each black hole is unique in its features. Even though they generally follow this 3-layer structure, the way they act can vary greatly. This makes them especially difficult to study using traditional scientific methods. Researchers can only study them by observing the radiation they indirectly emit or by examining the dust and gas surrounding them. Directly exploring a black hole would be considered futile, as anything that enters the event horizon is inevitably pulled toward the singularity, where it is crushed into nothingness. Despite billions of dollars spent on probes, collecting useful data from inside a black hole is not an option. Thus, scientists must study black holes in 2 dimensions, despite their 3-dimensional nature. Adding to the difficulty is the fact that no 2 black holes are alike. When studying them, we must account for the known breakdown of physics. Black holes offer a circumstance in which both quantum mechanics and general relativity must be considered. Theories suggest that black holes are created when massive stars break apart. As a star runs out of fuel and cannot continue producing enough energy to counterbalance gravitational forces, it collapses inward, leading to a singularity. To further study black holes, NASA scientists turned their focus to the region at the center of the M87 galaxy, where they spotted a massive whirlpool of hydrogen gas rotating at an incredible speed. This gas should have dispersed due to centrifugal forces, but it remained unaltered, indicating the presence of a massive object, most likely a black hole. It's thought that this object may have a mass 3 billion times larger than our Sun. Roy P., a New Zealand mathematician who died in 1963, utilized equations devised by Einstein to propose a significant theory. He suggested that black holes were rotating, rather than uniting into a single point as previously thought. A rotating black hole structure, like a thin ring, is known as the ergosphere. This matter-rotating disk is essential for understanding the breakdown of physical laws near black holes. Royer's model also predicted the existence of Einstein-Rosen bridges, or supposed wormholes, capable of providing an escape route through space and time. These theoretical connections could link distant areas of the universe or even different universes. To comprehend the idea of a wormhole, we must first understand Einstein's notion of spacetime. According to Einstein's theory, spacetime is a four-dimensional fabric warped by objects with mass, creating gravitational fields that influence the movement of other objects. Imagine spacetime as a piece of paper. Folding it makes a shortcut between 2 points. This fold represents a wormhole, a possible route through spacetime that could instantly connect distant locations. While wormholes are only theoretical and lack concrete evidence, they are a logical result of general relativity. Wormholes are unstable by nature, meaning they would rapidly collapse if formed. Despite this, the concept of wormholes, especially as a conceivable path through time or space, has sparked excitement among scientists. Belonging to the CR wormhole category named after Royer, these structures might, in theory, connect two far-off locations in spacetime, possibly even tying together different. This elusive theory of everything, one that unifies quantum mechanics and general relativity, has become one of the most sought-after goals in modern physics. Such a framework would allow scientists to explain the inner workings of black holes, wormholes, and other cosmic phenomena that currently defy full comprehension. Several candidates for this unified theory have been proposed. String theory, for example, suggests that the fundamental building blocks of the universe are not point-like particles, but rather tiny vibrating strings. These strings, existing in multiple dimensions beyond the familiar 3 of space and 1 of time, could potentially reconcile the differences between gravity and quantum mechanics. Another contender is loop quantum gravity, which attempts to quantize spacetime itself, implying that space and time have a discrete structure at the smallest scales. If proven, this would fundamentally alter how we view black holes, not as smooth singularities but as regions composed of quantum grains of space. One of the most tantalizing predictions of modern theoretical physics is Hawking radiation, proposed by Stephen Hawking in the 1970s. This phenomenon suggests that black holes are not entirely black, but emit tiny amounts of radiation due to quantum effects near the event horizon. Over immense spans of time, this radiation could cause a black hole to evaporate entirely. Hawking radiation bridges the gap between quantum mechanics and general relativity, but it also introduces paradoxes, like the information loss paradox. According to quantum theory, information about a physical system cannot be destroyed. However, if a black hole evaporates, what happens to the information about everything that fell into it? Is it lost forever, or somehow preserved? Physicists are still debating this question, and it has profound implications for our understanding of the universe. Some believe that information is encoded in the event horizon, an idea known as the holographic principle, which posits that the entire 3D contents of a black hole might be described by 2D information on its surface. This radical theory has led to fascinating developments in quantum gravity and even suggests that our universe itself could be a hologram, a three-dimensional projection of data encoded on a two-dimensional boundary. In recent years, progress has accelerated due to advancements in observational technology. Telescopes like the Event Horizon Telescope, EHT, have provided unprecedented images of black holes, allowing researchers to test theoretical predictions with real data. These efforts, combined with increasingly powerful simulations and particle accelerators like the Large Hadron Collider, are bringing us closer to unlocking the secrets of these mysterious entities. But as we stand at the edge of this knowledge, new questions arise. Could black holes serve as gateways to other universes? Are wormholes truly passable with the right form of energy, such as exotic matter with negative mass? Could time travel become more than just a science fiction concept? These questions remain unanswered, for now. But one thing is certain: black holes are not just cosmic curiosities. They are keys to understanding the most fundamental laws that govern our reality. As we continue to explore the cosmos, gather new data, and refine our theories, the secrets held within black holes may eventually illuminate the path to a deeper, more unified understanding of the universe itself. Is this required? This theory is often referred to as the theory of everything, a goal pursued by numerous physicists, including Michio Kaku, a renowned SCI scientist who has been working on one promising project for years. A strong candidate is superstring theory, which argues that subatomic particles are not point-like but are actually tiny, vibrating strings. Theoretically, these strings are thought to form the very fabric of the universe, explaining not only gravity but also the phenomena surrounding black holes. Despite its promise, superstring theory, and related ideas like wormholes, necessitate the existence of additional dimensions of spacetime that are so minuscule they cannot be detected with current technology. Even with the challenges in testing superstring theory, its mathematical elegance and coherence make it one of the most compelling ideas in theoretical physics. Simultaneously, scientists are exploring other approaches that could lead to breakthroughs in understanding black holes. For example, quantum gravity is another area of study aimed at combining the laws of quantum mechanics, which governs subatomic behavior, with general relativity, which explains large-scale phenomena like planets and black holes. By combining these two theories, scientists hope to acquire a more precise understanding of how quantum gravity works and better comprehend black holes and other cosmic phenomena. The intersection of general relativity and quantum mechanics becomes especially significant when studying black holes, particularly near the event horizon, where gravity is extreme. A theory that can explain both quantum effects and relativistic effects within the interior of a black hole, where the singularity exists, remains one of the greatest challenges in physics. The singularity is the point at which space and time are so warped that physics as we currently know it no longer applies. A unified theory is needed to comprehend this, capable of reconciling quantum mechanics with general relativity. This need has led to the development of theories like loop quantum gravity and other quantum gravity models. As we continue our investigations, one thing is clear about black holes: the more we learn, the more we realize how much remains unknown. Black holes are not only sites of destruction but also locations of immense complexity and potential. Some theorists suggest they may even be portals to other dimensions, perhaps the key to understanding space and time itself. Black holes remain a critical area of study. As our methods and theories evolve, so too will our understanding of these mysterious objects. One of the most promising recent advancements has been the observation of gravitational waves, ripples in spacetime caused by the motion of massive objects, such as black hole mergers. By detecting and analyzing these waves, scientists can now study black holes and other cosmic bodies in ways that were previously impossible. Gravitational wave detections have already provided new insights into the behavior and dynamics of black holes. Future experiments and mergers are likely to offer even more revelations. In addition to gravitational wave research, the use of advanced telescopes and imaging techniques is another exciting development. The Event Horizon Telescope, EHT, which captured the first image of a black hole in the M87 galaxy, demonstrates how cutting-edge technology can provide fresh perspectives. By combining data from multiple radio telescopes across the globe, the EHT captured the black hole shadow, offering us a glimpse into one of the universe's most mysterious phenomena. As technology improves, we can anticipate observing black holes with even greater precision, revealing more about their structure, behavior, and role in the cosmos. The study of black holes is not just about understanding strange objects in isolation, it's about exploring the fundamental principles of the universe. By studying black holes, we're learning more about the laws that govern spacetime, gravity, and the very nature of reality. In conclusion, the study of black holes embodies one of the most thrilling and challenging areas of modern physics. Each new discovery brings us one step closer to unraveling the mysteries of these cosmic giants. Whether through gravitational wave analysis, imaging technology, or new theoretical frameworks, black holes continue to captivate the imaginations of both scientists and the public alike. As we delve deeper into these enigmatic entities, we may be on the brink of unlocking some of the universe's greatest secrets, perhaps even answering questions that humanity has pondered for centuries. Ongoing research into black holes is leading to a deeper understanding of not only these mysterious objects but also the broader workings of the universe. The more we understand, the clearer it becomes. Black holes are far more than just cosmic phenomena. They represent crucial pieces of the puzzle that may lead to answers to the most profound questions ever asked. Our exploration into these mysterious entities may very well hold the key to some of the deepest cosmic mysteries. The next great frontier includes refining our observational tools and theoretical models. Recent advancements in gravitational wave astronomy have already made significant progress. By analyzing and detecting gravitational waves, ripples in spacetime caused by the acceleration of massive objects like black hole mergers, we are now able to observe their behavior in previously unimaginable ways. The discovery of these waves has provided groundbreaking insights into the dynamics of black hole collisions. Researchers are optimistic that further studies will lead to even more thrilling revelations. Additionally, cutting-edge imaging and telescope techniques are opening new doors in black hole research. The EHT made history by capturing the first-ever image of a black hole in the M87 galaxy. This achievement, made possible through the global collaboration of radio telescopes, allowed scientists to observe the shadow of a black hole, offering a glimpse into one of the most mysterious phenomena in the cosmos. As technology evolves, we can expect even higher-resolution images, delivering deeper insights into the structure, activity, and role of black holes in the grand cosmic scheme. Indeed, black holes serve not only as fascinating cosmic entities but also as laboratories for testing the fundamental laws of physics, especially at the intersection of spacetime, gravity, and quantum mechanics. Through black hole research, we are not only expanding our understanding of these unique objects but also pushing the boundaries of what we know about the universe itself. These investigations hold the potential for breakthrough discoveries that could fundamentally reshape our understanding of reality.